Welcome to step 4. You've made it. Congratulations. We've gone through the first 3 steps of a test hypothesis. In step 1, let's quickly review. We identified the null and the alternative hypothesis we wish to test. Something like we want to test to see if a population mean is equal to 100 versus the alternative that it differs from 100. So we're trying to figure out which of those 2 hypotheses is correct. We're going to collect some data. And in step 2, we calculate a test statistic, or I guess more correctly, we're going to let the software calculate a value of the test statistic. I don't want you doing the math for the test statistic. It's basically a z-score. What we saw earlier in the semester, at least what we're looking at so far, is a z-score. It gets more sophisticated than that, but for our purposes, we're going to calculate or have the software calculate a test statistic, and it's going to give us a single number. That's what we're going to use to try to figure out which of those 2 hypotheses we believe are correct. Now, the way we evaluate that test statistic, that's the 3rd step. And in the last step, I talked about 2 different techniques. I talked about one at length called rejection regions, which is what we're going to be working with in the short term. And then I'm going to come back and I'm going to talk more to you about another technique called the p-value approach, which I like better, you'll like better, but we're not ready for it yet. There's some other stuff we got to do first. We're going to take a look at some examples. So thinking about this rejection region idea, the test statistic is what the sample's saying. The rejection region is kind of our way of understanding what the sample is saying. So the rejection region sets up a z distribution or a t distribution or some other curve that we'll get to later, where we kind of separate that curve into 2 parts. What's expected if the null hypothesis is true, and what's unexpected. And what's unexpected leads us to reject the null hypothesis. So the first way of making a conclusion, let's see if I can scroll through here, is the rejection region approach. And what we're going to do is compare parts 2 and 3. We're going to compare the value of the test statistic that we observed to the rejection region. And the rejection region, again, we're going to be looking at this normal curve, this t distribution, where we know what's expected. The rejection region says, yeah, don't look there. Look over here. Look what's not expected. Is that where the test statistic is? And so we look to see if the test statistic actually falls in the rejection region. One of the examples I did in the step 3 video was at alpha equal 0.05, we're going to reject if our test statistic is bigger than 1.645. That was the critical value. That was the value of what we found in the table. Well, is it? Let's take a look at our sample. Let's take a look at our test. Is it bigger than 1.645? If it is, we're going to reject H0. If it's not, if the test statistic is 1.8, it's bigger, we reject. But if the test statistic is 1.4, it's not. And so we're not going to be able to reject in that case. And so that is how we're going to use a rejection region. Now, there is another approach. It's called the p-value approach. Whoops. And again, when I talk about p-values in a future section, I'll also mention how we make conclusions. And again, the p-value is really easy. For rejection regions, we compare 2 numbers, the test statistic to the rejection region. For the p-value approach, we're going to compare 2 numbers there as well. But I'll get to that again in a future section. Now, when we compare those 2 numbers, that's one of the conclusions we can make. And this value of alpha here, well, that depends upon what we're working with. And we've talked about how the values of alpha can be between 0.01 and 0.10, but this would be true, this first statement, alpha equal 0.05 we reject, if the test statistic actually falls in the rejection region. So if the rejection region is reject, if z is greater than 1.645, this is when you get a 1.7 or a 2.0 or a 15. But what happens when you have a value of like 1.4? We're going to reject if the test statistic is bigger than 1.645 and we see 1.4. Well, some things we talked earlier about makes you want to think, well, that's when we accept. Ooh, but we don't. We're not going to accept. If you remember, I'm going to go back now. When we talked about identifying the test, we talked about some conclusions and consequences in a test hypothesis. So when we reject H0, there's 2 things. Remember, there's 2 things that could happen. We could either make a correct decision, which we're pretty excited about, or we could make what was called a type 1 error. And a type 1 error had probability alpha. Well, we know what alpha is. Alpha is 0.05. So when I reject H0, I know the chances of me being right. I know the chances of me being wrong, and I can live with that. The chance of me being incorrect, alpha, is going to be a small number. I'm okay with that. And if you don't like 0.05, you're like, ooh, that's 5%. I don't want to have a... Make it smaller. Make it 0.01. Make it 0.02. Make it some number that you can tolerate. When we reject H0, we know the chance of us being wrong. If we were to accept, if we were to say at alpha equal 0.05, we accept H naught when we have that test statistic that doesn't fall in the rejection region. It's like, okay, it's 1.4. It needs to be bigger than 1.645. Oh, it's not. Let's accept the null hypothesis. Well, you could go down that path, but here's what happens. Again, referring back to that little table I drew for you, when you accept H naught, you're either making a correct decision, which we're big fans of, or you're making a type 2 error. And the challenge we run into now is when you make a type 2 error, the probability of a type 2 error isn't alpha, it's beta. Remember beta? Beta was the probability of a type 2 error. Well, when we specify alpha, what happens is we won't know the value of beta. So if you were to go ahead and accept H naught, the chance of you being wrong is unknown, it's beta. And that's a scary proposition. And so we avoid it. We don't want to accept the null and have no idea the chance of us being right or the chance of us being wrong. And so what we do is we chicken out. We can't reject that. We can't say reject H naught because the evidence isn't there. We're afraid of accepting, and so we say we fail to reject. We cannot reject. We're not saying we accept. We can't reject. It's this no man's land where we're not really sure what the answer is. So we're just going to kind of default to the null hypothesis. At alpha equal 0.05, we fail to reject the null hypothesis. Now, you see FTR, H naught. That's the abbreviation that I'll use, FTR. Save some letters, save some time. So you may see that in the notes in the future. When you make your conclusion, you're either rejecting or you're failing to reject the null hypothesis. Now, one last topic on this slide. You do not want to get WOPed. W-O-P. You may see this in some form when you see your projects being graded, or you may have already seen it. But what does it stand for? Words of the problem. If someone's asking me to do a test of hypothesis, and I come back and say, hey, great news, at alpha equal 0.05, we can reject H naught, they're going to look at me like I have three heads. They're going to be like, okay, you seem pretty upbeat, Mark. What the heck does that mean? And so you need to go now and tell me what that means in the words of the problem. Oh, I'm sorry. There's sufficient evidence to indicate that the mean differs from 100. That was the example I talked about earlier. Mu equal to 100 versus the alternative mu is not equal to 100. There's insufficient evidence. If we fail to reject, there's insufficient evidence to indicate that the mean differs from 100. And actually, when you do words of the problem, we need an example. I don't want you just to talk about the mean. I want to talk about, oh, there's sufficient evidence to indicate that the mean price of all Mustangs exceeds $12,000. The mean rent of all Brandon apartments is less than $2,000 a month. We're going to use the words of the problem that we're working with. Now, this is something I want to help you with. So when we start looking at specific examples, I'm going to talk about the specific words we need to make the problem complete. So step one, identify the test. Step two, use the sample. Use some software to get a test statistic. Step three, for now, is the rejection region approach, where we identify values of the test statistic that allow us to reject. And then the conclusion is putting it all together. The conclusion should be an easy step. Should be a step where you just go ahead and it's a culmination of the work that you've done. So last thing I'll do on this video, and then we'll get out of here, is where do we go from here? Well, we go a lot of places, actually. Here are some applications. And usually business students take two different courses in statistics. Business statistics, it might be called data analytics. We have a lot of different names for these courses these days. But here's some things that you'll probably take a look at. And this semester, with me, we're going to do that. And actually, I can add a couple of other ones here. We also take a look at variances. We work with a single population variance. We work with comparing two variances. There's other distributions. So large sample test of a population mean, that's a z-test. Small sample, we typically think of that as a t-test. Here's a z. Comparing two population means, this could be a z or a t, depending on how it works out. Comparing two population proportions, that's a z-test. Comparing three or more proportions, it's a chi-squared test. Simple linear regression, there's a t-test, maybe an f-test. Multiple regression has lots of f-tests. But comparing a variance or working with a single variance is a chi-square, comparing two variances is an f-test. So there's other distributions that come into play. And that's the main reason I want to move away from. I like rejection regions. They're pretty straightforward, and it makes sense based upon what we've done this semester, especially when we're working with z's and t's. But as we get closer to working with chi-squareds and f distributions and other distributions, it's just more work. It's more distribution work, and the rejection region approach requires us to use the distributions. The p-value approach does not. Now, I know that doesn't make sense now, nor should it, but hopefully it will later when I go through that with you. So we'll look forward to the p-values. Our next step now is to go ahead and take a look at some of these applications, and that's probably where you're heading next. So welcome to test hypothesis. It's one of my favorite topics we talk about this semester. You can see we're going to use it a lot the rest of the way. So long.